Hello guys, in this video I'm going to talk about the discriminant functions and decision boundaries. So this was our decision rule that we used to take. If the probability of one particular class is the posterior probability of one class is greater than the posterior probability of other class, then we decide and we choose omega 1, or else what we do is we compare the risk. So if the risk is less for a particular class, then we choose the class which has the minimum risk, right? So in all these cases what happens is you have to compute two probabilities over here. In this case you have to compute two risks. So if suppose you have three classes omega 1 2 3 4 5, so then you'll have to compute that many probabilities and or else that many risks. So then people thought of what if we just divide the regions. So I spoke this in my video of normal density, that say suppose I have a like posterior graph like this. Say this is x-axis is nothing but some feature. Say during my example I have taken size to be one of the feature. So it is like we have these images of sunflowers and these images of rose, and what we do is we take a feature out of this image. So this is my training data, I'm using this to train. So I take a feature, so I have taken a feature, say size of the sunflower, size of the rose. So I have taken a lot of these samples, trained the algorithm, and I've got these PDFs. So this particular curve belongs to P of rose given x, and this curve belongs to P of sunflower given x. So here I in my previous video talked about this decision boundary over here. So here you can see that if suppose over here, how do I get to know about this boundary is basically where both the probabilities intersect. So the probability of rose and the probability of sunflower, wherever they intersect, that is my decision boundary. So why is this useful? This is useful because if suppose I know this point over here, say this point is some say 3, so then I don't need to now calculate the probabilities. If suppose my size is less than 3, I will say it is a rose. If my size is greater than 3, I will say it is a sunflower. So now there is no question of getting the probability of rose, the probability of sunflower, comparing them. Why to do that? You just find a decision boundary and get that number, whatever that number is. If it is less than that number, then it is rose, and if it is greater than the number, then it is sunflower. So please understand that here the computation reduces a lot, because you just have to find this number, one number, and for the whole data you can use this number and classify rose or sunflower. So this was for 1D case. So in 1D case you just need a number, but say for a two-dimensional case, what will happen is what we are going to look now. So let us take an assumption that we are going to use Gaussian distributions. So we are going to as we had done over here. So that was the whole point of explaining what is normal density. So we are going to use these Gaussian distributions, but we are going to use multivariate Gaussian distribution. So this is the expression for the multivariate Gaussian distribution. Now what I do is, to make computations further easier, I take the log. So the log gives one benefit, that this exponential reduces. Also there are some more benefits associated with it, with this, which we'll see further. So I'll define some g1 of x, which I'm going to call as my discriminant function. So this g1 of x is my discriminant function, and this I'm defining as some log of this probability. So this basically reduces my computations. It cancels this exponential, and we get this term over here. So this is for say class 1. So for class 1 I'll have mu1 omega 1 sigma 1 like this. For class 2 I'll have omega 2, sigma 2, etc. So now the point that I want to make is I want to find a decision region or a decision boundary. So say for a 2D case like this, I want to find which region. So this is my x1 feature, this is my x2 feature. So these plots are plots of features, right? So and my test samples will be something like this. Say one of the image. So here we are considering a two feature case. So I am going to take the size and the luminance. So if suppose I have done with the training, I have got this model, and I got a test image over here which has some size 3 and luminance say some 5. So that will be a point in this image, in this what we say plot. So it'll have say 3 over here and 5 over here, so that will be a point somewhere over here. So like this, every test data will be a point in this plot, right? So what I want to do is, instead of calculating these probabilities, what if I just give a some sort of Lakshman Rekha sort of decision rule, so which says if suppose your test point lies before this, it will belong to this region or this Gaussian, whatever it is. Say it is some omega 1, this belongs to some omega 1, and this is omega 2. So let this be say rose and this be sunflower. So if my point lies anywhere over here, I will classify it rose. If my point lies somewhere over here, I will classify it sunflower. So this is the purpose that I am going to define the discriminant functions and the decision boundaries. So we'll look at this case by case. So we'll see how the decision boundaries are made. So let us take a case 1 where I am taking the covariance matrix. So here the mean is not a problem, mean is just a point. So this mean will just decide where these Gaussians are going to be placed. But the covariance matrix is something that will define the shape of the Gaussian. So that is important. So I am taking a case 1 where the covariance matrix is sigma square I for every particular class. So I am having a circle. So because sigma square means equal variance on both the sides, so x1 and x2 are having equal variance, so this forms a circle. And since for both the class my covariance matrix are the same, hence the circle's radius will be the same for both the classes. So this is the case 1 that I am taking. So if you look at the discriminant function, so I am just putting this value over here. So these two are just written over here, and I am instead of sigma inverse, so here there will be 1 and here there will be 2. So instead of these, I just have a sigma square I inverse. So sigma square I inverse will just give me I over here upon sigma square. So that I does not make any meaning because I is just identity. So I have not written it, and this is what happens. So by this you can see that now gi of x, any g1 of x or g2 of x, gets this form. So because this gives you nothing but the Euclidean distance, or what we call as the norm of a vector. So this is just distance normalized by variance. So what this tells you that any point in the space, you just calculate the distance, whichever will be the minimum distance that you calculate as that particular cheese. So we are going to further elaborate this in the k-means algorithm. So please look at my video of the k-means algorithm. There we will going to elaborate what this distance actually means. But for now, here what we are interested in is we have to equate both the probabilities, that is g1 and g2, to find this point. So when I equate g1 is equal to g2, I get this point, and that is what I am interested in. So there is some algebra that we are doing. So please go through this. I'll upload these notes in the drive, Google Drive, and put the link in the description below. So please go through this is just simple algebra. So what I'm interested is in the results. So when I'm equating g1 of x is equal to g2 of x, so what am I doing is I'm just finding the probability where both of them are equal. This is what I'm doing. So when I equate both of them and do some algebra, so this is a lot of algebra that is done over here. What happens is I get an equation like this. So I get some Vt where Vt is this, V is this, so this is the V transpose basically, and x minus x naught is equal to 0. So here x is my variable, x is the test sample that I am going to get, and x naught is this particular thing. So let us see what is the insight of this decision boundary. So here I had a case where my covariance matrix is equal to sigma square into I, which means that my Gaussian will become an ellipse from will become a circle from the top view. So this is the top view, this is x1 and this is x2. And what this particular equation tells me is that whatever will be my decision boundary, so this is my decision boundary, it will be a linear thing. Why linear? Because here there is no x square, x cube, there is x raised to 1. So this is a linear, a straight line for this 2D space. For a 3D or multi-dimensional, it will be a hyperplane. So this will be a linear particular decision boundary, and it will always be perpendicular to the line joining the means. So here V, you can see it is nothing but the line joining the means. This is mu1, this is mu2. So mu1 minus mu2 or mu2 minus mu1 will give you the line joining the means. So this is V, and what our decision is expecting is V transpose. So we are going to have a slope which is V transpose, so it is going to be perpendicular to V. So this is the insight that we get. If suppose this is my covariance matrix for all the classes, then I get a linear decision boundary which is perpendicular to the line joining the means. Also, if suppose my priors are different, if suppose I am more likely to have omega mu1 than mu2, so I am more likely to have, say, this is rose suppose, and this is sunflower. So suppose I'm more likely to have a rose, then what will happen is this decision boundary will start shifting towards the sunflower. So then this will be the new decision boundary, because if I'm having more if I'm more likely to have rose, then rose should get a bigger region, right? Then its probability is increasing, so it should have a bigger region. So that is why this equation says, as and when the prior of one particular case increases, your the decision boundary shifts away from that particular Gaussian where your prior is increasing. So here if say P of W1 is greater than P of W2, what will happen is this will be a number which is greater than 1. So say it is 2. So this thing will be positive because log 2 will give you a positive answer. So this term minus this will be negative. So this much is positive and a minus sign will make it negative. So what is happening, it is shifting the midpoint. So this point is nothing but x naught. So this x naught is giving you the location of where it is intersecting. So initially if the priors are equal, if both of them are say 0.5 0.5, so this will become 1, log of 1 becomes 0, and everything goes, and you get just mu1 plus mu2 by 2. So that is the midpoint. So if the priors are equal, your decision boundary lies in the middle. But if they are not equal, as in this case, if p of omega 1 is greater, so then what will happen, it will shift away from mu1. That is what is the significance of this. The other insight is that if suppose your variance is very small with compared to the means, So if it is something like this, say the distance between the means is too large, so this is say some mu1 and this is the Gaussian, and this is some mu2 and this is the Gaussian, and I have drawn this very small. Okay, I have drawn this very small because I am taking the variance to be very very small. So if variance is very very small, then mu1 minus mu2, so this basically just gives you the distance. There will be a square over here. So this just gives you the distance. So if the distance is very large as compared to this, then also what will happen is you can expect a decision boundary that is in middle of both of these. So if this is the case, the prior will not really matter. Even if this is the case, it will still be in the midpoint of the line joining the means. So that is the insight of this first case. So now let us take a case 2. So for case 2, what am I saying is, for case 2 all these covariance matrix are equal. So I am just saying that all of them should be equal. They need not be the variance need not be equal. So here there can be a case that there is an ellipse. So here you can see the variance in the x direction and the variance in the y directions are different, hence it is an ellipse. Also these are correlated, so these things are there. So because of this, what happens to the decision boundary is what we are going to see. So if you also solve this little bit of algebra, you get to know that this is also a linear decision boundary. So this will again give you a linear decision boundary, but the only difference that will come over here is now this angle is not 90 degree. Now this is some angle, this is at some angle. So initially when we had circles, when the variance were equal, you could see that we got perpendicular, which makes sense. This is quite symmetric along this. So here what happens is, because there is this particular kind of ellipse, your decision boundary will no longer be perpendicular to the line joining the means, but will be at some angle. Also it is important that it will be still be linear, and the same thing applies over here also. If suppose the prior of one particular class is greater, then the decision boundary will shift towards the other class, because it makes sense. The prior is greater, so means you are giving more probability to this, more this is more likely, so more region should come under this. So that is what is case 2. So this is the equation. So I just am giving an insight. You can go through this thing. This is very much mathematical. So the insight is the thing that is important. Next, let's go to case 3. So in case 3, what I'm assuming is I have some theta, some sigma I, which is different for all the 3 classes. So I can have a class like this for which the variance is very large, and I can have a class like this for which the variance is very small. So I'm assuming a different covariance matrix, and here say this is for rose and this is for sunflower. So here you can see that if suppose here you can see this is the equation that we get. So there is this term that we get, x transpose w1x. So because of this term, so this you can imagine as some x square term that is coming over here. X transpose into x is what is going to happen further. So this becomes quadratic. So because this becomes quadratic, now this is no longer a linear, which was the case before. So because of this, now the decision boundaries will not be a straight line. It will be some curve. So this can be any quadratic or hyperquadratic curve, where the decision boundary can be it can be a plane also, if suppose this becomes 0 by some case. So it can be a plane, it can be some hyperplane. So if you are talking about multiple dimensions, a hyper word comes down. So it can be hyperplane, it can be hyper ellipse. So here you can see that if suppose this is quite small, you can get a decision boundary like this, so it will be something like an ellipse. Or if this is big, so you can also get a parabola. So this will depend on how your covariance matrix is, and that will define how will your decision boundary will be. Also you can have a case like this where the means are coinciding but the variances are different. So in this case you can have a decision boundary like this. For the samples inside this region it belongs to this, and for all the outside it belongs to that outer class. So this is also what you can get. So here also it is possible that you get a circular or a spherical decision boundary. So all that we are doing in this is basically, without instead of finding the probability of each sample belonging to a class, we are just finding a discriminant or a decision boundary. If the particular sample lies in one of the region, it will be allocated to that particular class. If it lies in other region, it will be allocated to the different class. So let us summarize what we have done over here. So case 1 tells that sigma is the covariance matrix sigma I for all the sigmas, for all the classes for ith class, is nothing but equal, and that is sigma square into I. So that says that the covariance matrix is equal for all the class and same variance for both the features. So this is a circle, it is having same variance for both the features. So here what will happen is there will be a linear decision boundary which will be perpendicular to the both the means, and the prior will decide where will this be in the midpoint or will it be over here or there. That is what priors will decide, and this will decide sigma square upon the distance. So distance and the variance will decide. Other thing is that if suppose the covariance matrix are same for all the classes, it need not be equal in both the variance. So it is just same. So we could get a ellipse like this which has different variance, and this is also correlated because it is like this. So in this particular case what will happen is this may not be 90°. This can maybe less than 90°, greater than 90°, depends on how the the covariance matrix is. So that is what we'll have, and x naught will depend on priors. So if the priors are equal, this will be in the middle of both the line joining the means, and if they are not equal, it will shift somewhere. So case 3 tells sigma I will be arbitrary, so it can be anything. It can be small for one thing, big, it can be anything. So in this particular case you can see that the decision boundary, this is the decision boundary, it can be non-linear. So here you can see it is not a straight line, and it can be a hyperplane, it can be some plane, it can be hyperboloid, it can be hyperellipsoid, it can be hypersphere, it can be paraboloid or hyperparaboloid, it can be anything. So that was all for this particular video. Thank you so much for watching. Thank you.